of stuff. So my graduate student career started from this. The left picture to tell you is magnetic fields and how can you do to use the squeeze for various different applications. I pointed out two projects that I was involved in, and the lower one of them is I personally built the entire system myself. Okay, good old days. Your devices is only 1 centimeter by 1 centimeter. It's a very special type of substrate. We use the laser deposition tool, and most of people can probably make 1 out of 10. But Clark Group had this recipe that you probably can make a 1 out of 2. But when I was in Clark Group, we improved the process more. So my success rate was 100%. So every chips I made, it will ended up to be your devices. So then there are other projects want to do some other stuff at that time. They will ask me to make devices for them. So again, it's a 10 millimeter by 10 millimeter chips, right? We have the biocrystal. So I decided, well, since for other applications, they don't need these giant loops around, we can just utilize in that biocrystal, make a 10 squeeze in parallel there. So I basically can make a 1 chip for 3 projects to use. And that was my glory day. So at that time, 1996 to 2001, you're going to see a lot of my name associated with Clark Group papers for applications which I only make from that chip for them. Okay, so since I'm involved, the top one is the high TC squeeze to do low field MRI. And so people needed a squeeze to do that job. We originally actually pull out the squeeze from a dry box, which is someone made 10 years before me. It was still working, but the problem was the coupling was not good enough. And so then I then just make the reticle and then make the devices for the low field people to do their measurement. But my personal one is the lower one, say YBCO magnetometer. So that's the one that we found out if you pattern the film into this mesh, then the superconductor doesn't trap magnetic fields anymore. So your devices can be very, very stable and quiet and behave happily in the Earth's magnetic field. So you can use that for a lot of application. So one of them in my project, we shipped that entire copper mesh cylinder to Netherlands. And then we were doing the magnetocardiography. So basically just measure a human being heart. You might wonder, why would I want to fly my entire tour, go all the way to Netherlands for this measurement? At that time, there's a regulation. We were not allowed to do the human subject in the lab. So we could do is, if we have a mouse, we can do that. We can just put a mouse underneath. But we really want to demonstrate that it's a benefit for human beings. So at that time, there was only one lab in Europe that would take us. So we just fly the whole system. So the picture is at their lab. And then you can just lying down on the lounge chair, and then I could take your heartbeats at that time. So that was my thesis. So the whole thing is really enabled by, we will be able to make devices, really sensitive devices. As you can see, devices noise is the lowest bar ever. And that noise plot is in the middle here. So on the right is applied magnetic field, and then a vertical axis is the noise come out of the squeeze at 1 hertz. And so you can see I can apply magnetic field, the noise is still fine until somewhere around 100 microtesla. And that was sufficient enough to do this magnetocardiography without the magnetic shielding. So at that time, the people was already doing that, but they all need to spend $500,000 or $2 million to build this very fancy magnetic shielding room. But my tool, it's you don't need any room, you just need a copper mesh. So that's what the beauty of it. So that's how it all started. Single pixel, that copper mesh inside is only 5 pixels, 2 gray diameter, 3 single pixel. So then from there, I graduated. Then what do? Cosmology people came to me. So that's the Paul Richards, Adrian Lee, and Bill Hozaffer team at Berkeley. They actually did not come to me. They went to my boss, John Clark. They said, hey, we need to hire someone who can make devices for us and understand squeeze, because at that time we were also doing a frequency domain multiplexer. So John just like, yeah, I know someone is graduating. Maybe you could use her. So I literally just moved my office from across the hallway. So basically, it was still very close. So moving on to my postdoc career, at that time, everybody, all the cosmology people would try to use this material, superconducting material as a TES devices. The reason is if you put this piece of the superconductor weakly connected to your certain bath temperature, then you connect this TES to input coil of the squeeze. You constant voltage bias this piece of superconductor at its transition. If you have any optical light coming in, this dot bias point will move up because the membrane get heated up a little bit. So in return, the resistance will change. The resistance changed because we did constant voltage bias. So that means the current in this loop will change. And I told you just earlier, squeeze very sensitive, can measure magnetic flux, right? So the way I couple, any current change will become a voltage output from the squeeze. And I already know how to measure voltage output from the squeeze. So that's a piece of cake. The difficult part now is how do we make a TS? No one knows how people can make single pixels, but for cosmology project, we need hundreds, thousands at a time. And so it's really not a good job that you have to make a single pixel for 300 of them or 1,000 of them. So my life as a postdoc was to develop the array using the microlab. So you guys are too young probably to know about microlab. It's the Marvell NanoLab now, but it used to be called Microlab in Corey Hall. So I was there literally fighting over other users about do not put magnetic materials inside a certain chamber so we can deposit our superconducting films. So on the right, you see the two pictures. That's all from my old pictures. This is a TS. We have this gold ring that we can then slow down the reaction time of the TS. The whole design have to match it to how fast or slow you scan your telescope. And so that it would, this gold ring would, how thick we deposit that gold will determine the time constant of the devices. And lower part, you see, we make the array out of the 4-inch wafer. And this really all came out of the Berkeley Microlab at that time. So then what do we do? So by 2005, we delivered the whole thing to Chile first. So we have a project in Chile, and so that's a 320 TS. We have a multiplexer factor of 7. Then we were there for 2 seasons. Entire team will go there, assemble everything. So the door you see on the lower right, when we ship the whole door up there, believe it or not, we hear noise inside the door. And then we just like, oh my God, what do we do? So you see everybody was on deck. We were like taking everything apart, the screw get loose. And then it was rattling around, destroy all our super insulating things. So we literally was like a reconstruct the whole thing right on the side. So that was one fun project. And then the same array, but slightly different design, also was shipped to South Pole in 2006. This time you can see we have a 960 pixels. The focal plane is shown here. It actually takes this 6 triangles. And so what does that mean? It actually took students probably a couple years to just make the perfect 6, because Berkeley Microlab at that time can only do 1 wedge at a time. We were not able to do any batching. At the position etching is all single wafer process only. And so it took us a really long time to figure out how to do. At the end of the day, I realized one thing: I need a well-controlled clean room to do this job better. Having said that, Berkeley Microlab was very nice to me. I have the monthly lunch with their lab manager, so make sure they understand that cosmology superconductor was not big job, big income for them, but it's very important because you probably don't know, but at that time it was all about semiconductor fab. So we actually need to go to this small room, because they call the dirty room, because we have the gold. And so that was the time, right? We have to do that and then use that. So I would go to talk to the lab manager monthly and then make sure if the tool is down, they will fix it to our spec. But that was just a lot of work. Then people knew I can make devices. Of course, they came to me. The 3 national labs with all the cleanroom criteria. And so I decided to join NIST Boulder. So my career at NIST Boulder, 2007 to 14, literally is developing from zero. They did not have a TS program at that time, to single pixel that I show here. And then when I left in 2014, we had a process on 6-inch wafer. And then it can make almost 2,000 detectors on one wafer at that time. We got involved with a lot of projects at that time. But I want to say is my 7 years at NIST Boulder, the legacy I left there is the TS fabrication recipe. So this recipe show certain steps. You just need to do room temperature metrology that can inform you what your devices will be at cold. The reason I can do that is entire process. I identify 3 key points that I just need to run 3 cryogenic measurements, then I know exactly what I'm looking for at room temperature metrology. And this is some loop that no one ever done before. So when we first came out with this, people thought, oh, 2 years from now, your process would drift, it will be different. But guess what? NIST Boulder is still using the similar idea and the same recipe. So it's still working. If you have a robust, if you can really identify the issues correctly, I think that's the main thing. We can always measure, thousands of different parameters, but at the end of the day is what is the correlation? And then what can you measure in process? And that's the most important things. And that is demonstrated here. So I have the example on the right. The optical efficiency, people told us they want 90% or they want 100%. After we design, we would say by simulation, you can only get 70%, sorry. But then we would say, okay, then how can we make it better, right? Then we change our dielectric material, make it a silicon rich. So then you change in the index. Then by doing that, we can increase our optical efficiency from 70 to 90. And then the beauty of it, this is only a small project. It doesn't need you to make the entire devices to do. You just need to make a 3-layer process. Then you can do cold measurement, room temperature, and do the loop. So then when I really make these real devices, I know exactly what index I should see in that range, and then my devices will be the high optical efficiency. So that was the concept. So that was an example. So again, this is my glory days, and this is how I got an APS fellow. And then at that time, NIST Boulder was not the only place that has this process. I want to show you here is on the left side, the bicep cake array used a JPL fab. They were doing a similar idea, fighting for the same thing to make the array uniformity correctly. And then Berkeley has a team led by Toki to do the polar bear array here as well. And so the 2 boldy one, the ACT pole and SPT pole, that was the one that I produced from NIST Boulder. So they were, because in cosmology field, everybody needed arrays, and there were many, many people trying to make the good ones. So at that time, then I decided, well, since I can make the TS array as a recipe, people can use it. Why don't I do more for other superconducting devices? So I came to pitch SLAC 10 years ago, say, why don't we build a clean room that focusing on superconducting devices? So we call this clean room detector microfabrication facility, DMF. So this was actually 10 years ago, my pitch slide. We were going to say this is going to be the national lab Foundry. We were going to do a lot of stuff. In addition to CMB, you can see there's X-ray there, optical as well. We were going to do not only the quantum stuff, also amplifiers, spectrometers. All the pictures was at that time I collected that I believe it can be done in the clean room. And so this was the grand vision. Pitching to DOE headquarters, pitching to SLAC. It took a while, and then finally just coming down about 2019-ish, CMBS4 start forming and needed a foundry. So we pitch again internally. We show SLAC upper management that it is important to do the real good science. It requires superconducting devices to begin with. Then DOE needs to have a really good superconducting foundry for that. And so that was the pitching one. The pitching two is I got lucky. I wrote the proposal with a whole bunch of brilliant scientists. And in the proposal, I was the only one requesting to put a foundry inside, and we got the money. So I have all my equipment money came from the QNext Center. And that's how SLAC at the end decided, fine, we were going to build a clean room to host those tools. So that was kind of a 10 years ago, or not 2019 now, 2020, we have to write the state mission needs to start formalizing as a project. So as a DOE project, you always have to start with what is the mission needs. Again, you constantly keep hearing me saying the same thing. We want to build state-of-the-art clean room for superconducting devices. A clean room itself is not impressive enough. The impressive thing is we're going to focus on be able to identify the key factors so we can do the closed cycle room temperature and cryogenic metrology test. So then we will come out with the standard recipe for people. And then we don't have to keep doing R&D or keep trying out a deposition or whatever for future, right? So that's the beauty of it. So from there, we then have to think about what is the project requirement. This is a slide how we convince the SLAC, entire SLAC upper management, because it's not just the high energy division really want to do CMV, you also have to talk to the people in SSRL or LCS2 people that they just like, I don't really need TS, right? They have their own detectors already. So we actually had a project with SSRL to show them the TS spectrometer is actually pretty good. So to convince them. So we did all that at that time. Then finally deduced down to what do I need for this clean room? So this is the key performance parameters, and that has been everywhere for this entire construction project. What do we need? We say we need a class 100 because we want to make arrays, and if it's class 100, we believe that's doable. If it's a class 4, it's even better, but it costs way more. So budget is limited, even though everybody told me don't think about budget, but it is limited. It was limited. So the 100 was the one we believe we can make. I could relax to class ISO 6, I believe, which will be class 1000, but then we have to make sure that HEPA filter has to be directly above all your equipment. So I decided that was way too much trouble. Because what if 10 years from now, people want to repurpose the whole clean room? Then I have to think about for long-term use for this clean room as well. So that's why I said that's put the money to do the class 100. Vibration is very important for us because for quantum, we need to do a lot of small features. Having said that, our smallest feature we probably would do is probably somewhere just about 0.35 micron in the DMF. If I need to do anything smaller than that, luckily, just across the DMF, there is another clean room called NanoX, specializing in X-ray optics. So they have the state-of-the-art of the e-beam lithography there, and their feature size is 5 to 10 nanometer. So basically, if I told them I need something 100 nanometer, they would look at me and say, that's huge. So I'm good there. So I know if I need to do something smaller, I just need knock on the door across the hallway. So then background acoustic was one thing I never knew until I have to build a clean room. Turned out acoustic will cause vibration to the tool. So it's very important. And I told you about the NanoX has this 5 to 10 nanometer resolution. When they really do that, they have to turn down their HEPA filter to as slow speed as possible. Every people walking has to tiptoe to be as low as possible. And then when they're doing the writing, I cannot move. That was the thing. I just like, I cannot move. This guy, don't move, don't talk. So that's acoustic thing that affects their tool. Then the temperature, why does it matter? So turned out all the chemicals that we use, we need to pattern the films, the photoresist, the tool itself has optics, right? Like ASML has this alignment, the optics alignment. If you have a temperature gradient, this optics alignment will shift. So you will not get the resolution you want. And so that's why the temperature, humidity, it was all came from the photolithography requirement. You spin the photoresist. If then you pattern them, then if you have the high humidity, guess what? Your photoresist will absorb the water in the air, and then your 1 micron become 2 micron line. And it actually happened when I was in NIST Boulder. So we always have a sign, it say humidity is above 45%, do not enter if you are patterning something less than 2 microns. So we actually have that sign before. And so that's one thing I learned. Other stuff is more like just a utility support for the clean room that's necessary, like ultra pure water, the processed nitrogen. You will see something we call utility nitrogen is because the new tools for safety reason, all the electronics, they flow a lot of nitrogen. And so we realized that if we use the pure processed nitrogen, that's really costs us a lot for operation. So we buy the tool that can generate something that's not so good, but still good enough for the electronics. And that's called utility nitrogen. And then we also have the process vacuum, for a spinning truck and stuff. So then the key thing comes down, now I build this clean room for you. Sherry, what's your capability? Then we have to say, okay, what can we do? And this is more for the construction people to know what we will deliver. And then we say that's the end of the construction phase to turn over to operation. So all that took a long time, but we are there. At SLAC also like to cut entire project into phases, so we know how to track down the progress. So this entire DMF construction project, it actually has 4 phases, starting with empty room. How do we do called clean room fit up? Is put everything inside the partition, the piping inside. Then at that moment, when they were doing a clean room, I was in charge of doing the tool procurement. So I told you about, we identified 2 big needs, right? CMBS4 at that time, and then the content information. And so we laid down side by side, what's the tool requirement? And then how can we then match them and buy the minimum set with the money we have? So that was that, the phase 2. So 1 and 2 almost run simultaneously at that time in parallel. Phase 3 is after the construction is finished, and then we need to move the tool inside. How do we connect the tool to the facilities? So turned out that's the most difficult part in my experiences so far. There are so many details that even though we've hired a professional vendors to do the job, but they don't understand what's required for superconducting fab. Give you a quick example. I make a very, very specific note. All the process gases have to use this VCR connector. It's a very special type of connector. Because all our process chambers using that. So we decided we want to use the same connector. But this connector has this gasket in between, it's metal gasket. Okay, so you have a 2 connector metal gasket, and then you kind of bolt them together. The metal gasket, my experience is that people would not pay attention. They will use the one has a coating. And guess what's a coating? It's a nickel. So it's cheaper too. I don't know why. I guess they don't have to polish them. And stainless steel will cost slightly more. So I made it very clear, I'm happy to pay more. Please use the stainless steel gasket. They told me, sure, yeah, we hear you, would know your requirement. Okay. Luckily, the first time we connected a process piping, I was there. I insisted I needed to be there. They should show me if they know what they are doing. So they open a package in front of me. They put a thing, they tighten it, and then say, see, we know what to do. Then I pick up that wrapping paper, and it just says nickel coated right there. So guess what they already done? They actually done all the other piping, right, from our ceiling to the, we have this utility drop. I was just going crazy, so they actually have to come back, replace all of them. And that's professional people, just so you know. So that's why everybody knew as SLAC, I am super picky on that. So, so this is the phase. I am showing you about the management structure, kind of high level, because I am showing, so I'm putting my name in a straight line. If Zish is showing, he will put his name on the straight line because we are actually under construction, just so you know. So I shuffle his name to the other side. But during the operation, I would like to have the advisory committee that can help me for funding, also for deciding technical issues. And so those will be on the side, and that's the red box on the left. How we want to do the operation we're working on it, and how we work with other national lab or even other, the industry, we're still working on that as well. So I cannot tell you more at this moment. But I can tell you, come back to the clean room. So this is a clean room without the tools. It looks very nice and clean. We have the design that you can just see through the whole window in the hallway. And so you can see what people are doing. I also have millions of cameras everywhere. So if someone is doing something, the camera will trigger and then send me a text. So I can do that. So this entire clean room is about 5,500 square feet. And you will keep hearing me saying the same thing. I want to standardize the process because I believe there are huge room in all the superconducting devices that we can do that. There will be material issues, but how you integrate different materials together become a process. I believe there will be a key point that you can point out, and then you just need to check them constantly. You don't need to start from scratch every time. So that's my goal for this clean room. So you see the last bullet point is strongly correlated with specific cryogenic testing. So entire proposal when I pitch to SLAC, it's not just a clean room. I also ask for, sorry, okay. I'm going to show you a tool map, and then I'm actually going to also ask for metrology lab. So that will be the next one. So the tool map for the clean room is on the left. That's 5,500 square feet. I use color coding. I'm not sure how well that runs, but try to link them purple to purple-ish and blue to blue-ish. So that's the entire, so I just told you I bought the tool. So literally I bought probably 80 of them myself, talking to vendors, spec them out, going to vendor to check out the tool, make sure they run before they ship it to me. So that's the list. The both font size is the model. And so that's our entire tool set. And they are all inside the clean room, except the one I have the yellow light. And because that tool is up and running at Stanford SNF clean room right now, because when we bought it, SNF people just like, they cannot find that one. So they ask us, can they borrow it to use it? So we loaned it to SNF. So they are, that's why it's yellow. We haven't moved that one up yet. Rest of the things is all in the clean room. The metrology lab, currently, on the tool list, so you can see, we bought them too. It's designed to do cryogenic measurement. So we have a dilution refrigerator. We have network analyzer. We can do microwave, we can dice the wafer there. We can do wire bonding. We also budget into for future, put a probe station there. So that's that space that, this is literally just came out last Friday, and we're going to finish the 100% design, hopefully by tomorrow. So I am going to steer back talking about metrology thing. This is actually the slide that came from my colleague, Daly. He came out with this idea. He said, hey, in process measurement, which is the room temperature measurement that I've been talking about, the green ones, it's easy because you are in a clean room, your wafer came out of the tool, you can then immediately go and do the measurement. If you have to do cryogenic, there's a barrier and also the cost. You then need to have a cryogenic system. You need to have another person need to be able to dice and assemble the sample box and then be able to put into the system to do the measurement, right? And then if you need to do even more fancy measurement, that's the top one, and that takes even more money and time. So where is the balance? You can, like I said, you can do 1,000 measurements, but the key thing is what is the key ones? How do you identify them? That comes from experience, that comes from, I don't know, the in clean room that you have intuition about what you are looking at in Cleanroom. So my colleague has this, and we constantly talking about what is necessary that we should have for the DMF. Then we came out with this list. We believe it's very important that we should know what is the film thickness or etch rate. And so that's why we buy the profilometer. It's that can do that job. Our profilometer is semi-auto. And what does that mean is you put a wafer in, it can measure it by itself. You don't even need people to change the die and then measure again. It just does it on its own. But it can only do single wafer. I do not have the money to buy the cassette loading. If I could have an upgrade, I would love to. Then another thing is not widely known, but it was when I was in NIST Boulder, is niobium. It's a somehow very stressful material. Niobium somehow doesn't, if you're, when you deposit niobium, your shroud or your shutter gets too dirty. Niobium gets stressed. I don't know why. How can niobium know? But it just does. And then when it gets stressed, the TC is dropped down. And so what do? Then you measure stress. So we believe it's very important to have the stress gauge. Only for room temperature and only for the very stressed materials. In my process right now, I only identify niobium. I'm sure there are others. Aluminum really doesn't care. And so aluminum manganese doesn't care. Moly copper doesn't care. But niobium is one. And it's really funny. If we deposit, we check the stress all the time, right? If we then check the stress keep going up to some point, then the measurement go haywire, meaning it goes up and down like a scanning like that. Then we know, oh, you need to clean the entire gun again. So it's something no one actually cares, but we found out we know how to prevent that. And that's something I cannot put into paper either. But it is a very interesting factor there I learned. I just told you we do the silicon-rich silicon dioxide. So ULAM is a very important tool for us to be able to do R&D on a dielectric material. We have a probe station that allows us to probe the devices, how good they are. And then we also buy the microscope from Leica and also Keyence. I did not put the Keyence there. So Leica is really good automatically. It can do wafer inspection. It can take the pixels, stitch them, and then do the data analysis about, hey, you have this pixel A has a weird stuff on top, and then the pixel C has something else, and the rest of them may be good. So they have that whole software that can help us out. And that's why we buy the Leica for that purpose. And then important thing is the dilution refrigerator. We need to be able to do the quick feedback about our devices. And so everything we put on our dilution refrigerator for measurement is the basic property from Cleanroom. So what do I mean? For example, if I have a squeeze, I probably just check if the critical current is right, normal resistance is right. I would not check the noise of the squeeze, something like that. And because the noise of squeeze will be up to the project, whoever needs, and then they will measure that, and then they can feed it back to us. So this worked for me, and we believe it can apply to not only the TES fabrication, but also for other stuff. 10 years ago, my pitch was I'm sure I can help QB people to make the better fabrication. Guess what? 10 years later, people already figuring stuff out. But they're still not there yet. You can see a lot of papers from all the big companies when their single pixel data is still way better than the arrays. So I believe there's still room to improve, and I believe the DMF can still help out. So, but I don't know how fast. We have to kind of make sure DMF is up and running faster in order for me to be able to catch up. So the current status of DMF, you saw, we have all the tools inside the clean room. Some of them still wrapped with bubble wrap, but they're all connected facility-wise. We are asking the vendor to come back to do tool stops. Some of them already done, some of them are not, depending on the tool schedule. And then at the same time, for each individual tool, we want to define what is called baseline process. So for example, at NIST Boulder, we have this tool called SIS tool, superconducting insulator superconducting tool that can deposit niobium, aluminum, niobium. That tool has two recipes. One is standard 200 nanometer on silicon dioxide, what stress number will come out, and then they tell you the deposition rates. So if you need something for niobium 400 nanometer, you need to deposit for longer time, okay? So there's a recipe that's called standard recipe. The second recipe is about aluminum oxidation time, and that can tell you what is the critical current at your squeeze junction will be. So that is something I want to do at DMF as well. Define the baseline process for each tool, and the beauty of it is I only need to maintain the baseline process. The users then can build on top of it. And so we are working on what it should be the baseline process for each individual tools. Having said that, it's not just the deposition tool or etching tools. It's also photolithography tool. What I mean is we need to have a baseline on, for example, coating the photoresist, the tracks. We need to set up certain baseline, say, if you follow this recipe, uniformity will be whatever, and then the photoresist will be whatever thickness. And so that's called a baseline process. It doesn't mean people cannot change, right? I just told you, if you need to do something different, you can calculate from that and then do your own way. So that flexibility, normally you don't get from semiconductor foundry, but we can do that. As long as you don't bring your wafer with a nickel inside, then you can come and use it. So that's that part. Metrology lab, I just told you 100% design should be done by tomorrow. And then in addition to the hardware I'm telling you about, we are hiring people as well. We want to hire 2 scientists under the quantum initiative to work on the quantum information science. We also want to hire the 1 technician to help us maintain our facility. We already have the lab manager to make sure that entire clean room can be up and running, but we just thought it's really good to have the tech 100% under him. At SLAC, we also have the engineers and technicians from various different directorates. So we can, when we need someone to do engineer work, I can just call someone for help to pay them. So we have that ability as well. So a little bit outlook. Now we have a clean room. We have concept where we want to go. Can we go there? It turned out the most recent years, this has become the slides that everybody shows when SLAC have to report to DOE. So you can see DMF is very important. It's not just because I put it in the middle. It's also a lot of projects in DOE that interests projects now, and they all need to use a superconducting foundry. There is a project called QuantiSet. We heavily use that money to make devices. DMF itself got Stanford money, SLAC money, as well as the QNX money. So the QNX is down there. And then QNX is funded by BES. We also budget in CMBS 4 will be one good place to help out. And Zish yesterday in a meeting just told me we might have to make 1,000 wafers. So all that, there are way more we can do. Like I say, it's all about compatibility of the devices or process. We can help out a lot. And the beauty of the uniformity, if we can really achieve that, in the same process, we can even make millions of different devices on the same wafer. And that is something at NIST Boulder we would do too. My same TS wafer, if someone say, hey, we just need few single pixels, we will team up with other projects. We can make a whole wafer and supply for multiple projects. So that is all possible. So this, it turned out to be not so bad internally at SLAC, but it doesn't mean we don't want to work with people. You can see we have the project money coming from various different places, and then we work with various different national labs. So we all open up to do more lab connections and more collaborations. And then the QuantiSet I told you about, it is very, first, a superconducting fab, I know the money that can support R&D. And so Ideally, at that time, the funding was to make devices to support dark matter search. But it's quantum superconducting devices, so it just fits into the DMF portfolio. For long term, we are pitching in that they should support DMF directly, so DMF could become their foundry as well for their science people. And so we're still working in progress on that. And then this is just a big broad, just a nice picture to show you what DMF could do for future. These are the professors who came to us, and they really are interested to be able to make devices not just once, but multiple times. It's interesting that in my life, like I just told you, I have a 100% success rate when I was a graduate student. My devices all came out very good, so I never needed to make more to get the good ones. My 10 devices on that tiny 10 by 10 millimeter wafer, the 10 squids, they were all identical. So basically, that's why I didn't need to make more. So my goal is be able to, again, come out with the process, help people. And so if professors come, they want these devices, advanced coherence junctions. Now, if we have the process, I want to keep it. And so 5 years from now, you come back, we can make the same devices for you with the same quality. And that's what I want. Like NIST Boulder 10 years later they're improving a lot. But basically, the Cleanroom was still doing the fabulous job there. And that's what I want to do too. But more than just TS or more than just a squid readout, I want to do something different. So my summary, but I have another tiny bit of something I want to tell you. So this is a summary about DMF. And DMF, it is efforts came from SLAC, Stanford, and BES funding. Without these three together, we would not be able to build that Cleanroom with where we are. We believe DMF will have a major impact, including actually way more than what I wrote here, but this is just because I didn't know how much more I can put in here, so this is what I can say for now. But lastly is, again, the pitch line again. I know I have not demonstrated at DMF yet, but I have done it before, and I know how to do it. And I really, really believe that DMF can do a really robust, well-controlled, and reproducible fabrication for the whole entire community. So with a little bit time, I just kind of want to run through a really cute project that I'm working with Professor Ken Irwin at Stanford. We're making these superconducting devices that allow us to do a dark matter search. So this is a team. The people are updated currently. First group are senior people, and then middle group is a postdoc, and then lower group is the graduate students. And the picture was taken in 2022. We do not have an updated one, so we probably should get another one. So the idea was SNOMED's report. It actually pointed out clearly in the green boxes area, if you want to reach the sensitivity to that area, you need to have a really, really good quantum sensing. What does that mean? Can I just use a squid to do that? No, squid still just a standard quantum devices. You need something better than squid. You need something can do squeezing, right? So like a qubit. So that's why this green box is very important. And that's the Quantisat money came out to do the R&D for this type of the research. So with that, we got the money, and then we then say, what can we do? Well, Ken Irwin said, then what can we do? So he went into this plot on the axion masses versus the coupling. And then, you can see the green ones is the known data. It's already published. And then he said, hey, we have a huge empty space. We can do something using some new devices. And it is true. Oh, sorry. I have to say one point, data point is a John Clark. When I was in Clark group, that's happening. And when I was in Clark group, make these superconducting devices called MSA, microstrip amplifier. And that impacts ADMS from 270 years to only 100 days. What do I mean? Replace the solid state amplifier to a superconducting amplifier. The same frequency band for before you need to scan for 270 years. After you use the superconducting MSA, you only need 100 days. now it's way better. This is the old data, again, my student time, so now it's way better. So this was a striking point to people in the dark matter fields about, wow, we can use superconducting devices to shorten the time and finally can have a graduate students. Otherwise, no one will want to work on this, 270 years to get your paper out. So that was a good data point. Anyway, so Ken say, hey, we have this giant space. We can design something differently. And that's why he came up with this dark matter radio. And I'm not going to tell you the idea. We can always invite someone to give a talk about that. Again, my job is device physicist. Is how can I make devices to help them do this measurement? DM radio has 3 projects. DM radio 50 liter in yellow, DM radio cubic meter in blue, and then there's also in proposal for the gut. The devices, that's the one I like. This is the one we work, almost done. So idea is, why don't we take something we already know, but make it slightly different? So the device is called RQU, it's in the middle. And you can see instead of the 2 junctions in parallel, I have the middle line. So literally, it's the same superconducting Josephson junction design. You place them differently, and that came out to be a really good devices to measure really good sensitivity signals. So this is the picture from last year. The new picture I cannot show you because students want to publish on the March meeting, so they will not give it to me. But March meeting is coming. And so this is the data from last year, that's proof of concept. We have it. We know we can inject signal, and then we can see the signal come out, how much improvement and how much is the suppression in noise. So for example, here, the student told me they can suppression down to 29.6 dB. So the devices I told you, if you use a squeeze to use this RQU, we are 29.6 dB more sensitive. And that in turn can get better in the line. And that's something that we believe we can do. So that's it. Oh, so I just want to show some pictures, that's all.
Thank you so much. Let's thank our speaker. Thanks. We're going to take questions. So those on Zoom, if you have a question, please raise your hand and you'll be called on. And whilst those in the room think of their questions, I have one for you. So with this guarantee of 100% yield for every device for the DMF, when the DMF is up and running and commissioned, how can folks at Berkeley, get some time working at your facility? So for example, here at Berkeley Lab, we have the Molecular Foundry, which is a user facility. Is the DMF going to be run like a user facility where people submit proposals, or is it more for internal collaborations?
That's something we're still working with the director right now. And
Okay.
so that's why I cannot say. Yeah.
Okay.
But you will come out soon. Yeah.
Okay, great. Yep. Okay, we'll start right here.
With the fab, how are you doing data management? You went through your set of tools for measurement and such, and then your wafers and travelers. What type of ideas do you have for data management?
For what type of?
The data management. How do you, your sample, when you take all your measurements, how do you correlate them to your samples and keep track of everything?
Very good point. A lot of time for devices, you don't know until the end, meaning endpoint science people do the measurement and something goes wrong and come back to us. So we identify optical efficiency thing. It actually came from, we just use a standard recipe to begin with. But then the people with the TS detector people do the optical measurement and found out that, hey, efficiency was only 50%. Then we did a simulation, found out, oh, with the current, whatever parameter should be 70%, we still drop 20. But at that time, we say, well, why don't we see how can we improve it to become better? So at the end, it has to be the devices first to come out to tell us what went wrong. Yeah. We do. Each devices, each wafer will have its own paperwork. Yeah.
Okay, we're going to take one from online and then Michael and John. So Allegria.
Hi, I was interested in your thoughts on which of the many processes you mentioned are most sensitive to magnetic impurities, which are a typical kind of distinguishing aspect of superconductor clean rooms. And then the other kind of related question is, you mentioned getting rid of the nickel, but stainless is like 10% nickel. So I'm just curious if there's something special about stainless that makes it less of a problem.
So stainless steel, we have to specifically pick the 316L, and just because that is more stable and it's electropolished. So when you don't have the rough surface, your gas can flow, and hopefully it doesn't carry too much particles coming out. Magnetic particles, it's actually really tricky. One thing, believe it or not, I cannot avoid is the nickel again. Our entire dry air, compressed air in the clean room needs a filter because from the facility has oils, particles, so what's not good enough for our process. So then we need to do the filter. Design team, construction team decided to pick a filter inside element is nickel. And so they, without telling me, they already bought that, they already installed that. So down the road, what I can do is then I buy the Teflon inline filter to block that out. So I actually, it's become better and better in inline filters nowadays. So that's one thing we can do. If you cannot avoid, then make sure you have the inline filter right before the tool, and that can help you out. Yeah.
But so is that a documented problem for some specific process?
Yes. So here's the thing. A lot of people, okay, so give you an example. When I was at Berkeley, this is really Berkeley example. TS, you show earlier on picture, it's aluminum titanium TS. There was a really old chamber. Sometimes we deposit the wafer was fine, sometimes wasn't fine. And then we look into who did the white film before us. And when we were not fine, it's because there were people before us did iron. So somehow someone did an iron, you would think they got coating on the whole wall. It should not be on my wafer, which I come in, I clean them, use I've cleaned, then I deposit titanium aluminum. But guess what? Every time we see TC will be only factor of 2 lower. But if no one is doing an iron in front of us, then our TC will be beautifully fine. So those were something we saw. And then we also had a problem once. Someone designed some new shutter, and the shutter has a gold coating, but underneath the gold was nickel, and we didn't know, and that caused a problem. So that was another example I have. And personally, for squeeze frequency domain multiplexer, the generation 0, we have the printed circuit board to mount the squeeze. Students was really nice. They did not want to polish the copper pad, so they do the gold plating. Beautifully, gold doesn't oxidize, so we can just wire bond anytime we want. But guess what? Underneath the gold at that time was nickel. And then our squeeze, none of them were working. So this is, again, more data point that I can accumulate. So that's how we know that's very important for us to minimizing this kind of magnetic interference to our process or measurement.
All right, let's take a question from Michael and then John, and that's probably the last.
Yeah, thank you. I guess my question is, so you spent some time talking about, making consistent wafer development and putting them out for things like CMBS4, which are going to require a lot of fab, while also doing stuff, R&D testing, for example, like the transbond qubits that will go into DM radio. And I'm just curious, like how you plan on balancing, standardization for like high output, large projects with these R&D small focus, like the transbond qubits or, future TS development. Let's say, Noah Krinsky has an idea, like how you would balance that, or if some other people wanted to come and use that, how hard might it be for us to get space in there? Kind of like Rebecca's question.
Because currently we are designing our clean room to be the wafer fabrication. So if you only have the substrate is 10 millimeter by 10 millimeter, for example, it's going to be difficult for you to come in. Then I would recommend you can use the tour in the campus, because the Stanford campus has a really good superconducting fab as well. But once you want to do a bigger area, I can guarantee we can help you out on that.
Okay.
Yeah. Cool. And then if you are using on a silicon wafer and standard recipe, meaning your qubit junction critical current is the same as, say, the other group, we can always make on the same wafer, like a chocolate box. And then we just peel off for you. Yeah.
Cool. Thank you.
Thanks for the talk, Sherry. I'm wondering, now that you've gone through this whole exercise of planning out a high throughput superconducting specific fab, it was just mentioned magnetic particles are a problem. You of course talked about cryogenic, rapid turnaround screening. Are there other things that you identified that are kind of different from conventional semiconductor foundries that are of note for, how the DMF would be different from some semiconductor focused thing?
I would say most of the stuff are pretty much similar. Yeah. Material compatibility is a key thing, right? They don't like us because we have a gold. But we
Okay.
don't like them, they have a nickel, so.
Thanks.
Okay, unfortunately, we're out of time. So if you have any further questions, please contact Sherry.
And if you want to see the clean room, please do come to SLAC, and I'm happy to show you around.
Lovely. Okay, let's thank our speaker again. All right, we're going to stop here and the recording will be online soon. Thank you.